Okay, we are back to COMSOL Multiphysics in its default appearance when you just start it out. What I have in mind now is to solve a two-dimensional heat conduction problem with otherwise more or less the same structure as the previous one-dimensional one. So I start by pressing 2D here. I go on with the arrow for the next choice to be made, and that is again heat transfer. And I press the plus sign here to add this selection to my selection of physics. I press the arrow again and I pick stationary as before, and then press the finish flag. Okay, now I have to specify my domain, which is now a two-dimensional domain. What I have in mind is a domain which is more or less a square like this, but with the right up corner off the domain. So a domain looking like this, a square, but I would like to cut off here a quarter of a circle. So I will do that exactly as I said. By starting with the square here, I left click this one, and I now simply draw this square. It starts at let's say x equals 0 and y equals 0, which is here. So I left click the mouse here and I simply drag this to be a square extending up to let's see now, well, like this. Fine. This is the unit square. Next, I would like to subtract or define a circle to subtract here. And this circle should have its center up here and have a radius, let's say 1/2. So I pick this type of circle where I specify first the center point and then mouse drag to specify the radius. So I start here, left click, and I draw a circle which has radius 0.5, like that. You could also specify these different domains by choosing or specifying them by formulas up here. If you right click here, you can pick, for example, a rectangle or a square, and you have a possibility to specify these domains using formulas, using numbers. Now we did it with drawing instead. Now I will pick both of this domain, the square and the circle, and I will then try to subtract the circular area from the square area. So I now pick these two in the right order because I would like to subtract the circle from the square. So I first pick the square. This is what I would like to subtract from. And then I press the control button and left click the mouse on the circle to make two choices. And then I go up to the menu here where we have the difference operation. We take the square area minus the circular area. So I left click this, and then the circular part of the square disappeared. So this is now my domain, and you could of course easily do all kinds of operations using these options here. Now we would like to specify the physics in this domain, including the boundary conditions, and we would like to make a mesh, finite element mesh, and we could start with that because that is simple. So I left click here on mesh and I build the default type of mesh like that. Of course, you could influence the size of the elements, have a fine mesh to get a good resolution and so on. And you could also have a fine mesh in part of the domain, as we discussed in the slides. But we now proceed to specify the physics. So I look at what I have to do here, I activate this one with a left click, and I will look at the equation, and you see that the differential equation I've chosen here looks more or less the same as before. We have to specify the heat conductivity, and we go for exactly the same values as in the one-dimensional case. So this is 1, and I put the density also to be user-defined and be 1, and the heat capacity as well. Sorry, I have to make the big 1 like that. Fine. Next, we would like to add a heat source. So I left click here to add a heat source. So I right clicked first, and now I left click to make my choice. I also have to specify where this heat source is active. There is no choice here, so I can left click in the domain and add that to my choices. And I specify that the heat production is uniform and constant and of intensity 1. Okay, now all the physics in the interior of this domain is specified, and I will proceed to specify the boundary conditions. Again, we have thermal isolation as default settings on all 5 parts of the boundary. We have now 1, 2, 3, 4, 5 parts of the boundary. And the default setting is thermal isolation on all of this. What I would like to do now is to add some temperature conditions. So I right click here and go down here, by which I can specify temperature condition on parts of the boundary. So on where do I want to specify this? I can start with select all boundaries and then deselect the one where I want to keep the isolating boundary conditions, and that is the one over here in my case. So I left click this one and I deselect with a minus sign this from my choices. So then I've picked 4 pieces of the boundary, and on these pieces I would like to specify a condition on the temperature looking like this. Temperature capital T is T0, and I specify T0 here, in this case to be 0. Now all specification of the problem are now made, and I can proceed to compute the solution. So I right click on study and left click on compute, and hopefully then I would get a graph of the solution popping up now. So this is a color graph where different colors represent different temperatures. So dark red represents 0 Kelvin degrees in this case, and the lighter the color becomes up to white represents warmer temperatures up to 0.05. I could visualize the temperature field in other ways. We have this one, for example, isothermal contours. So I double click this one, and then in the graphic windows here you have these isothermal curves representing different temperatures. You also see some arrows here, because if we look here, this choice here includes, in this case, both contours and arrows. I could delete some of this and add different options here. If we look at these arrows, what do they represent? Well, we can see it here that the arrows represent, the arrows has an x component and a y component. The x component is the x derivative of capital T or the x component of the gradient, if you like, and the y component is the y derivative. So in other words, this is the temperature gradient. So these arrows point in the direction of increasing temperatures, and that is actually what you see here. They point into the light white area here where the temperature is highest. You could have these arrows represent something else if you like. For example, we could have the arrows represent the heat flux. Then we know that the heat flux goes in the opposite direction of the temperature gradient. And the heat flux is also proportional to the heat conductivity. Now we pick the heat conductivity to be 1, so the heat flow would be simply minus the gradient. So I can just put in minus signs here, and then I can redraw this, redraw the plot by left-clicking this up here, and the arrows will shift direction and point in the direction of the heat flux instead. So heat is now flowing out from the hottest area here in the direction of the boundary where we have a zero boundary condition. So heat is leaking out of all parts of the boundary except this one to the right, where the temperature stays constant across the boundary because of the isolation. We could also, of course, take away the contour lines, if we like, here by right-clicking this and simply delete this from the graph. Are you sure that you would like to delete the contours? Yes, and then we are left with only the heat flux arrows. I think that is all for now. A quick view of what you can do in the case of a multidimensional problem.